Thank you for reminding me there. Okay, so the session is being recorded, so I will post that. If I, it takes a little while after the lecture to before they make it available, but so if I forget to get it uploaded, somebody please send me an email and I'll get you the link for it. As far as this link for the main class, this collaboration link is the same. As far as I know, it's not going to change for the entire semester. So this is just the collaborate link for this class. So I plan on using this same link for all the rest of the classes that we're going to be doing. Okay. All right. So I wanted to remind you that the exam is on Thursday. Okay, so the exam's going to be through Blackboard, and so I've already scheduled it. I've already, let me see here, I was working on it earlier today, and so we're down here in week 10, okay, and so it, we look at the settings, you can't see it right now because I still got to work on the exam a little bit, so it's not open yet, but it's going to be open on March 29th, right, which should be Thursday. Oh no, that's the due date. I'm sorry. Okay, yeah. Thursday is the 26th. Okay, so yeah, so it's going to be available on the 26th. I guess I said that on the previous screen, hopefully. Yeah, so March 26th after 5 p.m. Okay, if you want to take it earlier, let me know and I'll try to have it ready, but I made it 5 p.m. so I have a little bit of time to just kind of go through and work on maybe adding the questions and stuff. So it just takes a lot more time getting the questions into Blackboard, especially into a manner that I try to set up as many as possible to be automatically graded, which will make my life a little bit easier. So, but the exam has a time limit on it, so you only have 2 hours. Once you start it, you have 2 hours. Okay, so it's going to open up at 5 o'clock on Thursday, but you don't actually have to take it Thursday. So I'm giving you a window from Thursday at 5 o'clock until Sunday night. Okay, so March 29th is like Sunday night. Don't wait till the last minute. Okay, this is the time you have to be done with it. All right, so since you've got 2 hours to work on it, you better be starting before 10 o'clock on Sunday. But I highly recommend don't wait till the very last minute, because people have done that before, and then for whatever reason Blackboard stops working or something like that, and you can't do it. So try to start it, or complete it Saturday or Friday or something, and don't wait till the last minute unless you absolutely have to. Okay. All right, so we kind of get this crazy thing going on here when I share the screen, but okay, so where did my, all right, so just as a reminder, the exams, I guess I bring us back here for a minute. So, the exams are comprehensive. So I'll just kind of start by doing an overview here of everything we've talked about. So we've talked about the analog signals. On week 1, we talked about analog signals, talked about the difference between digital or analog. Remember that analog signals are between two limits, all right? And so, I usually have that question in there somewhere, and I'm looking for that keyword of limits. We can use current signals, and the advantage of current signals is that they do not attenuate. Or we can use voltage signals, which, of course, the voltage signals do attenuate, so you need to keep it close so that you minimize any attenuation. So if you're trying to run to the PLC halfway across the plant, there's a lot of attenuation, a lot of resistance in those wires that'll drop your voltage and it'll affect it. So that's why we prefer to use current signals. We also kind of talked about instrumentation. Okay, so instrumentation was just one of those fancy words to basically mean an analog sensor. All right, and we also kind of talked about those converters that we've been using especially in the last few labs. We used that a couple of labs ago. We used that Red Lion converter, a PID converter. We hooked RTD to it and lots of different things. Okay. We also talked about power supplies. So we have linear power supplies or switching power supplies. And we kind of talked about, last week, or not last week. Yeah, I guess it was last week. When we talked about the load cells and I talked about filtering and stuff. And, I think the problem with our compact logic PLCs, they're so noisy with those load cells because they actually have a switching power supply attached to them instead of a linear power supply. All right, so I'm going to just kind of go through the different weeks here and do a summary. And if you have any questions, write them down here, and then I'll flip back over. Because right now I can't see the screen because I'm just kind of going through this browser window here. Okay, so just kind of make a note of it or put it in the chat window, and then I'll come back and look at those as we go through. But the next thing we talked about was numbering systems and PLC networks. And so, there's definitely going to be some questions on the exam for converting from decimal to binary, from binary to hex, or from hex to binary, or all those various different types of conversions. We also talked about the 2's complement. So remember, like, to store a negative number, okay, the method they came up with to do that is what was called a 2's complement. And the reason for that is because building a binary adder circuit is very, very a simple circuit. It's can be done with just a few standard logic gates in a computer, and it works very well. But to do subtraction, to build a subtraction circuit, to worry about borrowing for every single bit and stuff, I tried to show you that in class. That got really kind of complicated quick. And so subtraction circuits for even an 8-bit number, the subtraction circuit is just, I don't know. I never really tried to build one, but I did try to do like a 4-bit one, and it got so complicated. It was like, what's going on here? So trying every time you add just one more bit, it like doubles at least the complexity. But the adder circuits still remain kind of simple. So what somebody figured out was that if we do a 2's complement, so if we have a negative number, or if we have a positive number but we want to subtract it, the best thing to do is actually to negate the number and store it as a 2's complement, and then we can simply use an adder circuit and ignore the very last carry, and the math works out great. All right, so 2's complement circuits are very nice. Okay, so and then we also talked about networking. We talked in general about some of the various networking protocols, like the Circos, is a fiber optic network, and then we talked about like device net and control net, and then those are all open. And then we talked about the closed loop protocols, and the two that I mentioned were just remote racks or the Data Highway Plus. Those are proprietary or closed protocols. If it's not one of those two, then it's probably an open sort of protocol. All right. And the most common one that I'm kind of seeing come any new equipment, they really tend to be pushing this Ethernet/IP. And part of that's just because everybody understands Ethernet IP pretty well nowadays, especially for IP version 4. And so, and plus, like if you need a switch to plug in multiple devices, you can go out and buy a switch for, you know, very, very cheaply. You can get a pretty reliable switch. So, so people have been kind of varying away. I mean, there's a lot of device net and control net and things like that out there, but you're seeing a lot of the new stuff go to this Ethernet IP. All right, so I was just kind of trying to check to see whether there was any questions out there. All right, so on week 3, then we pulled out the ControlLogix PLCs and we talked a little bit about them. So we talked about some of the differences. The Compact Logic uses that 1769 chassis and uses tag-based addressing. All right. Had a built-in Ethernet card. The ControlLogix are really designed, obviously, for a larger sort of application. So you can plug in a lot more modules to them. So you can buy various chassis. So they have they actually use what's called the 1756 chassis, and it has either a 4, 7, 10 or 13 or 17 slot, and we actually had the 17 slot chassis in there. But they also use the tag based, okay, but they didn't have, at least the PLC that we had didn't have a built-in Ethernet onto them, so you actually had to use one of those slots to use an Ethernet connection to communicate. And then we talked about the analog cards. We talked about the analog to digital conversion, and I showed you like the circuit for that. And then we talked about the digital to analog, and I gave you a circuit for that. And we talked about how technically what happens is it's taking that analog signal that's ranging between those two limits and converting those into a binary number. All right. Then we had the first exam, and then after the first exam, we had scaling. So you know, and that's of course is probably one of the more challenging parts of this class, is just trying to do the scaling. So the load cells are a good example of that, because when you get a load cell, especially like the load cells we have in the classroom, they've kind of been abused a little bit, I think, by the original lab instructions were saying use too high of a voltage for one thing, and so that wasn't doing them any favors. And so some of the load cells in the classroom aren't very good anymore. They you know, if you don't have anything on your load cell, you would expect it to be reading 0, and yet those load cells read some pretty high values even when you don't have anything plugged into them. So it's critical that you go through the scaling process. So the general equation for that is the slope, the line for the equation for a straight line is y is equal to mx plus b, where m is your slope. So you need to basically take 2 readings and then calculate what that slope is. And then from there, you can also calculate the intercept. So remember, the intercept B is, I don't see it written here, so let me pop up Notepad so I can type. All right, so B, so we have Y is equal to mx plus B, where B is that intercept. So you have to take 2 points, so you take and find out for value x1, what is y1, or for value x2, what is y2. And so if you wanted to calculate B, you stick in those points. So you have something like y1 is equal to m times x1 plus B. All right, and then of course that would give you the equation of B is equal to y1 minus m times x1. Or you can use the other point. It doesn't matter which point you use, you should get the exact same value. Just type it in here, y2 minus m times x2. All right, so it doesn't really matter, but most of the time, if you choose the y1 and x1 point, a lot of times, at least x1 is probably a 0. So if x1 is a 0, then you can simply ignore, then this part goes away, and then B is simply whatever the y1 value was. That's your intercept. It's that simple. Or sometimes x1's not a 0, but maybe y1 is a 0. So it's, typically you want to choose the x1, y1 point because you can simplify calculation of B. But either way, you should get the exact same B. And that's actually kind of a good way to double check your work by calculating B with one point and then calculating it with the other point and make sure that they came out to be the same. All right, so again, if you have any questions, just go ahead and type them in here, and then I'll just check every once in a while as I'm going along. All right, so then on week 6, we talked about those transducers and converters. Now remember, transducer is just that fancy word for an analog sensor, but we talked about some of the different types of analog sensors. Specifically, we talked about load cells, we talked about thermocouples, and we talked about RTDs, resistive temperature devices. So we kind of talked about that, and there were some other ones in there. We didn't spend a lot of time on the other ones, but you should just kind of know like what they are for. Like a tachometer reads RPMs, revolutions per minute, or something like that. So you should know that, but you don't necessarily have to know too much more about it. All right, and then we talked about human-machine interfaces. Okay, so HMI, human-machine interface, and we talked about for the Allen Bradley, which is the one that we use, their human-machine interface is the called Factory Talk, and we talked about how to set that up. And then of course we had our lab with that, where we took our 2 load cells, wired them into a converter, wired those converters into the PLC, did the scaling to scale our weight. So we used our test weight, that 5-pound test weight, and second point with no weight on, and then we were able to take those measurements and scale that and get our ladder logic working, and then we built that HMI. All right, and then last week we talked about integrators, and we talked about how basically when you're integrating, you're calculating the area under the curve, and usually your horizontal value there is in respect to time. Okay. And then we also, on Wednesday, I talked about the function block diagrams, and so I kind of went over that, and I was kind of maybe planning on at least talking a little bit more about that tonight since my recording didn't work. I forgot to hit the record button. So I'm going to kind of go back over and do some function block diagrams. But before I get into that, does anybody have any questions? All right, so nobody's put any questions in there yet. So let me just kind of remind you about the function block diagram. Okay, and so like here we kind of started off in the slides, and we had this just talking about ladder logic. And with ladder logic, of course, you have your power rail on the left-hand side and your ground rail on the right-hand side. And then we have our contacts or digital switches usually here that are tags or that represent signals coming in or virtual bits inside. And then we use ands or ors or nots to make a decision. And then the action would be maybe energizing a relay to turn the light on, turn a motor on, enable a timer, something like that. Okay. But then with the function block diagrams, now we're using these function blocks. So we have like a function block for an AND block, for a OR block, and that kind of thing. So we have to have our kind of input tags coming in here, and then we connect those together through this function block, and that generates that output. And so I've got one uploaded here right now. So not that one. So this right here is our standard fill-in circuit for using a function block diagram. So it's our standard fill-in circuit using the function block diagram. And so one of the things you got to notice here, right, is we have this feedback. So we have the output of this AND block, which is our stop, which is ANDed with either the start button or the fact that our relay is energized. So our relay turning on the red light in this case is energized. Okay. And I've got this filter block just sitting there, but it's not connected. It's not doing anything. Okay. So let me go offline for just a second and slide this out of the way. All right, so this is just our standard fill-in circuit, just this portion of it here. Those blocks I had just kind of thrown on there last week to talk about. So remember here, when you look at these, you just connect these. All right, so to connect this, you just kind of, okay, I'm going to take my start button and I'm going to connect it to an input. All right, however, for my second input into the OR, that was this output bit. So I need to bring that over here and connect it there. And then the big key here is because this input to this BOR01 block has an input coming in from a push button, which is no problem, but it's got its second input, which is actually the output of the AND block. And so now there's, the first time you try to run this, there's this question. I'm trying to say either the start button or the red light is a 1. But the question is I have no idea what the red light is because I haven't executed this block yet. So we have to click on this, right click over here on the line, wasn't on the line, okay? You got to be on that line and then right click and you have to do this assume data. And then when you assume that, would do that assume data, it puts this little like double arrowhead piece here. And that tells it to make the assumption. So the first time around, so the only issue is during that first time, okay? Once we've made this assumption and evaluated the logic, the next time we know what the answer is. It's a 1 or a 0. We know that. It's just for the very first start, the very first scan of the program that we have to worry about this assume data piece. Right, so we have to do that assume data. Now, if I don't assume data, so see now it's checked, I'm going to uncheck it for a minute, and I'm just going to come over here and I'm going to download this to my PLC. And I'm just doing this to remind you that if you didn't do that assumption, you're going to see some error messages pop up here. Okay. So I tried to download it, but pretty quick there, I get this unresolved loop. Okay. And then they're telling me I can resolve the loop by changing the data flow indicator. Okay. So there's a good test phrase for you. Data flow indicator of one wire in the loop. So this wire is showing you the way the data is flowing. All right. And so again, we need to click over here, make sure you're on the wire, right click, assume data available. Okay. And so now then when I try to download this, okay, and it's downloading to the PLC. Actually, it was waiting to pop up a message to ask me if I really wanted to download. All right, and so now it's downloading. Okay, and now since I had that error message, it goes into remote program mode. All right, so it's this got this like cyan color, so it's not actually running. So we got to remember to come over here, flip it back into run mode, and then for the function block diagrams, you see you get these green bars all along the worksheet area here, telling you that hey, we're live now. Okay, and then of course it turns green over here also. All right. But you got all this green, so it's really kind of hard to miss that it's not there. So now let's look at our fill-in. Okay, we have our start button is not being pressed, so it's a value 0. All right, and then we've got this value of our red light, this value we're sending out to the red light. Well, what is that? Well, we've already ran through this several times, okay, but the very first time we didn't know, so it basically just assumed it's a 0. So we have a 0 for the start, we have a 0, our red light is off, okay, so a 0 or a 0 gives me a 0 out, okay, and the stop button, of course, is the physical button on the PLC, and it's wired closed. So even though nobody's pressing it, it's wired closed, so it's feeding a 1 as our input. So we've got a 1 coming in through the stop, but our start is a 0 and our red light is a 0. So 1 and a 0 is a 0. So this is just maintains this 0 here. Okay. So, but if I come over here and I right click on this, and I go to monitor force value of start. Okay. And so I can come over here and I can come over here to my start, and under the force mask column, under monitor tags, I can force that to a 1. Okay. So if I force that to a 1, as soon as I hit enter, we're going to see that the red light I guess it's still not forcing yet. I got to come over here to IO forcing and say enable my forcing. Yes. And so as soon as I did that, then we see that I'm forcing the start button to a 1. So they even change the color for us here, which is kind of nice. And so therefore the red light immediately goes to a 1. So I've got a 1, or initially it was a 0. So a 1 or a 0 gives me a 1 out. A 1 and the 1 of the stop, 1 and 1 gives me a 1, so I get a red light. So my red light is turning on. All right, so again, this is just your standard ordinary CILN circuit, but it was written using function block diagramming program instead of a standard ladder logic. Okay, so it's the same logic, but written using function blocks. And we do that so that you understand the ladder logic for CILN. So I think it helps you see the differences and the similarities between function block and ladder logic. Okay. As I stated last week, honestly, I'm not a big fan of all this. You got to remember, you got to like do that right click here and do that assume data available and all that kind of stuff, where we didn't have to mess with that in ladder logic. So and I think somebody even asked the question last week, why do we do function block diagrams, or why do we have so many different choices of programming languages? And the answer, to me, at least part of the answer, is the fact that certain languages really lend themselves to certain tasks. And ladder logic does a lovely job of the CILN circuit. It's straightforward. You don't have to worry to remember to right click and do an assume data and things like that. So it's just all straightforward and easy to read and pretty easy to understand once you've done it once or twice. Okay, so if I come back to my tags, I'm going to force my start to a 0, but of course it doesn't change my red light because it's sealed in. But now if I force the stop button to a 0, then the red light, of course, immediately goes to a 0. Okay. Now I'm going to pop up here and just turn off my forcing. All right. And so I'm back to the original circuit. All right. So so one thing to remember here, though, is, this is, when you look over here in your controller organizer, this is our controller organizer, and under tasks, we have our main task. And under main task, we have the main program, which contains program tags and the main routine. And then to create the function block diagram, I came over here, I did a right click, and I created a new routine. So I did a right click on main program, select a new routine, and that's where I can select the type of routine, whether I want ladder logic, sequential logic, function blocks, or structured text, right? And I give it a name, and I could create that. All right, so that's how I created this function block CILN. However, the program always starts in the main routine unless you disable it, and then it'll start in the other one. But by default, it's always going to start in the main routine. So we had to come into the main routine, and actually right now under the main routine, the only thing that I did was I added this jump to subroutine. All right, and so if you remember, that was way over here on our choices. Okay, and I can't change it right now because I'm online, but if I go offline and we come over here to, I think it's still thinking here for a minute. Okay, but when it gets totally offline, There it goes. Then we go to program control, and then under program control, I was able to grab this jump to subroutine and add the jump to subroutine. And then if you have multiple subroutines, you would select which subroutine you're going to jump to right here. Okay. So in this very simple example of just a fill-in circuit, all I had in my ladder logic was the jump to subroutine. And then under the function block diagram, I use these little tags over here, which are called input references, to create my input reference for a stop button and an input reference for a start button. It could be an analog. They don't have to be binaries. These are just whatever tags that you have defined. And then you create your blocks. So when you're under the function block diagrams, you'll have your selections up here at the top will change, and so you'll have these function blocks that come in. So here's another AND button, for instance. I just added that to the work area. All right, but you notice that by default it has 4 inputs. Okay. And so since it's got 4 inputs, if I was not to connect all 4 of them, then my output would always be a 0, because I'm saying it's got to be input 1 and input 2 and input 3 and input 4. All 4 of them would have to be a 1 or a high to get a 1 out. Okay, but if I click on this little ... in the top right corner of the box, I can come over here and tell it, no, I only want 3 inputs or 2 inputs or however many inputs that you want on that block. Okay. Now, if a block is just sitting here and it's not connected, it really doesn't hurt anything. I can just go download it and the program should just run fine. And those things are just over there, collecting dust. Well, maybe not really virtual dust they're collecting. All right, so you can see I can download this, and I'm not going to get any error message because it just understands that they're not connected, so it's just basically going to ignore them. All right, so the text on this is pretty small to read, so I'll put my glasses on here. But all right, but that's pretty much the function block diagram for the fill-in circuit. Okay. I did talk a little bit about if you're doing integration, which we talked about last Tuesday. We talked about integration, and part of what you're doing with integration is you're trying to find that area under the curve. And to do that, you basically have to have a timer. And so a function block actually works pretty nice for that, because they actually build in the delta T timer into the function block. So they, instead of having 3 or 4 or 5 rungs of ladder logic, they just have that all built right in there. Okay. All right, so another option is a low pass filter. Okay, and I'm going to take this offline here. All right, and so I'm going to flip over. On the other window, I actually have the filter. I have that. This was the lab that we did with the two load cells. So remember, I've got this actually connected up in lab. Okay, so sitting in lab right now in C205, I've got 2 load cells. And so I've got the first load cell connected to input channel 1. And I've got the second one connected to input channel 2. And I'm using a compute statement. So this is doing my scaling here. So I'm scaling these load cells. And so this is my slope times my x, which is my input coming in from on my analog channel 1. Now remember, the if we look at the configuration of these channels, right, when you configure your input, you first have to turn these things on, right? If you don't turn them on, you're not going to get it. You can select whether it's a current or voltage signal, and you can set a filter to 5 hertz or 60 hertz, okay, or something in between if you want. And you can use engineering units or whatever. But when you do engineering units, because these things are bringing in milliamps, but engineering units multiplies it by 1,000 and makes it microamps. So if we look at the logic over here, I'm dividing by 1,000 to convert it back from milliamps into microamps. Okay, and so that's why I have that 1,000 divide by 1,000 in there, because they're scaling it because it's an integer number. Okay, so let's look at the tags too, just to remind you. So input channel 1 and input channel 2 are 16-bit integers. So there's no decimal point in those. Okay, so there's no decimal point, and so if you had something like 4.27 milliamps, well, you don't want it to just show up as like 4 milliamps, and so therefore they multiply it by 1,000 to give you the resolution. Okay, so but you have to remember, therefore, inside of your ladder logic or whatever, you need to divide that 1,000 back out to get it back to milliamps. Okay, so here I'm using the very first 2 rungs in there are compute statements. And these 2 compute statements are taking the binary converted number, which was in milliamps or technically microamps. It's converting it back to milliamps by dividing by 1,000 and then multiplying it by my scaling factor to get it into pounds. And then I'm storing it in a value called weight 1. Now notice weight 1, if we look at tags again, weight 1 is a floating point. Okay, so weight 1 is a floating point number, which means it has a decimal point in there. And so it is fractional, if you will. It's got a decimal point. It can be 2.7 or 4.7 or whatever the value might be. But the problem is we bring this in, as I said earlier, because I've got such noisy power supplies on those PLCs, the numbers really bounce around. So let me just go ahead and download. Well, no, I don't want to download this yet, but you guys hopefully remember from the lab yourself or from last Thursday how this load cell, this weight value bounces. Okay, so this weight value just really bounces around. So what I do then, I'm moving the input and storing it in a value called weight, which effectively has units of pounds. Okay, and then so I do that in the first 2 rungs, and then the 3rd rung I'm like, okay, now I've got these weights, weight 1 and weight 2. I'm going to jump to a subroutine called filter input, and if we look at this is using that low pass filter. Okay, so this input is therefore my input is my weight 1, and I have an input of weight 2, but then I have my frequency, which is, if you remember, we just looked at the frequency of the card. The card wouldn't let us go below 5 hertz. And so what I'm doing is I'm setting the angular frequency to be about 0.1 hertz here. So I've really slowed it down so this isn't letting very much noise in. And so we saw, and I'll show it to you again here, when I do download it, we saw that it ends up balancing out and the first few digits don't move once it's settled out. Okay. And so I'm filtering, I'm taking and storing the weights. I'm storing the scaled value as a weight, which effectively has units of pounds. And then I'm filtering weight 1 and weight 2. So what I'm filtering is weight 1 and weight 2, and I'm feeding those through the low pass filter, and then it's coming out and being stored in a new tag called weight 1 underscore filtered and then weight 2 underscore filtered. Okay. Then when we come back to the main routine, I can go ahead and like calculate my total weight 1 filtered plus weight 2 filtered is equal to my total weight. Okay. Now, the one thing that I want you to kind of notice, right now, all the weights are 0, right? Because I haven't downloaded or executed this program. However, when I do download it, you're going to see, if you watch these numbers closely, when I first download it and it first starts to run, you're going to see these numbers kind of grow, right? Because they're at 0 and they're going to grow. So what you're going to notice with weight 1 and weight 2, boom, within one execution cycle, with one scan of the PLC code, they're going to be at what values, which is should be somewhere around 2.5, but as we see, they bounce up, bounce down. They're bouncing all over the place, but they're going to immediately jump up to that 2.5 and be there. But what you're going to notice here with the filtered values, okay, because we're running them through this box, okay, the filter is a very slow filter, so it's actually going to take a little while to see them settle down into that 2.5 range. I think the one's more like 2.6, but 2.6 for weight 2, 2.5 for weight 1. So you'll see that take a little while to settle. Okay. So let me just do that. So I'm just going to go ahead and download this, and we're going to watch those. Okay, I'm going to go back to this so we can see the weight 1, weight 2 box and the total, and then the filtered values right below it. And so I'm going to go ahead and download this to the PLC. And once it gets downloaded, then we'll, like I say, watch these 2 boxes over here. Okay, so it's downloading, and then it's going to ask me if I want to run, and I'm going to say yes. All right, and then these boxes will start moving. So again, this top one here with just weight 1, weight 2, and total, those are going to jump immediately to whatever value and stay there. But notice these other ones, this one's 2.5, so it got there pretty quick. This one, but it's 2.51, 2.499, okay? And the filtered is 5.15, okay? But let's just watch it for a little bit. You'll see these ones are just continuously bouncing all around, okay? But as we let this one settle down, you see it reached 5.2, and I haven't seen it drop back below 5.2 since, well, okay, it hit 19 there, 5.19. All right, so, but it's just kind of takes it a little while to get there, because that filter, one of the things that filters do is they kind of slow, a low pass filter, anyhow, a low pass filter really slows down whatever value, whatever information is going through it. Okay, so that's why it kind of took it a while to settle. I mean, it didn't take it a long time because it's a pretty simple filter, but it did take it a little bit. Okay, but we see, like, again, up here, the unfiltered values, which actually they are filtered at 5 hertz just at the input card, but that's not nearly enough filtering because we can see it's bouncing from 4.6 up to 5.7. It's all over the place. But down here at the filtered value, we do see it bouncing around, but 5.19 to a 5.21 is about all that I've seen it change. All right, so it's saying much, much more constant. Okay. All right, so any questions about the function block diagrams? Again, the beauty to me about, okay, well, we got function block diagrams, we've got structured text, we've got ladder logic. The beauty, I think, is shown right in here because we can blend them together. So when ladder logic makes sense, you can do ladder logic. And when you need to do a function block, well, then you do this jump to subroutine, come over here, jump to your subroutine, execute that subroutine, and then when this, you know, when it does one calculation of everything in this subroutine, it jumps back in here and it finishes executing the ladder logic. Okay, so it's really nice with this software is the fact that I can blend them, so I can make use of the advantages of all the different languages. And, you know, because some of them are really good at certain things and some of them, you know, it's just kind of almost like people, right? You know, some people are really, really good at one thing and that same person's bad at something else, call it something B, but somebody else is really good at something B. And so, you know, it's kind of the same with these programming languages. They have their strengths, they have their weaknesses. Okay. All right, I don't see any questions yet, so I'm just going to continue on. One thing that I did not show you on Tuesday night, and I don't know, I know some of you have worked a lot with some PLCs and stuff, so you may know this, but some of you have never seen this before. So what I'm going to do is I'm going to go offline here, okay, and I'm going to flip over to my other program, and the only reason I'm doing this is I want to reset, because remember, even though I just went offline, okay, and this is something I don't think I talk about too much in class, but it's very important to remember that even though the software is offline, the PLC is still up there in Canton running this software. It's running this program. It's running the main routine, jumping out of the main routine and executing this function block diagram piece, and then jumping back to the rest of the main ladder logic routine, and it's running through this every, you know, microsecond or millisecond or whatever. It's executing it, it's executing it, it's executing it. Right now, as I'm talking, it's executing it. When we were online last week and we did these different programs and I downloaded them, I think I was in the function block or in the load cell one. So what that means is that, you know, after we signed off last Thursday, this program continued to run up there at school in room C205. This program has been running all weekend, right? So even though I'm not connected to it online live, it is still up there running, okay? So what I'm doing right now is I'm going to flip over to just this fill-in circuit piece, and I'm going to download this again, which is going to overwrite the load cell program. And the only reason I'm doing that is that that's just guaranteed to force everything back to zero, okay? Because when I'm downloading a completely different program, so this is going to wipe out all the tags that are in the load cell program and replace them with the tags that are in this program. Okay, so I'm just going to download this and I'm going to run it. So go back to run mode, and then I'm going to go offline here. Okay, so now, but the thing is, again, to remember that the tags running on the PLC right now are these tags dealing with this Silin circuit, and you know, it's ignoring all the analog inputs and all that because they're not even set up for this program. Now I'm going to flip back over to the load cell one, and I'm going to download this and go online here in a little bit. But before I do that, okay, before I do that, I'm going to come over here under my controller organizer, and I'm going to go to trends. Okay, and I know that you guys have all probably used an oscilloscope from one time to another, or even if you haven't, we talked a little bit about trending in the HMI last, well, I guess it was a couple of weeks ago when we talked about that, but you can do trends in the HMI. One thing I've never shown you, I don't know if maybe you saw this in PLC 1 with your professor then or something, or some of you may use this at work or something, but this trend will allow you to monitor and graph. Basically, you can graph anything in this program. So this is kind of cool. So I'm going to say new trend here, and this is just going to be, I want to see the difference between filtered and unfiltered. So I'll just give it a name here. I'll just call it show diff, and then give it a description. Show the differences between filtered and unfiltered. Okay. Now, and then we can set up a sampling time here. So we can come up here under the sampling time. Right now it's 10 milliseconds. 10 milliseconds is really quick, okay? And so what I'm going to do is I'm going to change this to seconds, but I'll make it, I don't know, we can change this later, it's no big deal, but I guess I'm just going to say, give me, well, no, let's just go ahead and keep it at 10 seconds then for now. And like I say, you can come back in and edit this. Now you get to pick your tags. Okay, and so you actually, now I never talked too much about this before either, so I'm going to flip to the other window for a minute and just talk about tags. Okay, so I always like to use the program tags. These program tags here are local to everything in the main program. Okay, if you come up to main task, you can actually create a brand new program. And then that program can have its own tags. Okay, and then you also have way up here at the top, I never really talked about them, but there's something up here at the very top called controller tags. The controller tags are basically just, they're global tags. And so if you double click on the controller tags, by default, the only thing you see under the controller tags are just your physical inputs and outputs. Okay, and so these are my physical inputs and outputs, and they're right there. Okay, and they're always up there. And they're available to any and every single task that you create. So if you come over here and create brand new main program, well, main programs there, you can't create a new main program, but you can create other programs by right-clicking here and say, give me a new program, and you can make new programs that have routines under them. All right, but your controller tags are always going to be visible to them. So the controller tags are like global to all tasks and all routines running in all those tasks. where the program tags down here that I always recommend using are local to just this one task. So if you're, if you're got a large, if you're thinking about the factory floor and you're doing lots of stuff with this PLC, you want to break it down into subtasks, right? So it's just like if you think about just even the class, our class, we break it down week by week. We talked about analog signals. Then we talked about, analog sensors one week, and we talked about HMIs one week, and we break it down step by step. I don't try to teach you everything for the entire class the very first day. And so the same thing, most things that you're trying to do get pretty complex. And so to help control and handle and manage all that, you break them down into tasks, and then you break those tasks down into routines, as I did here. Okay. And so those are your controller tags. So now going back to the trends, so when we try to set up our trends here, it's the scope. By default, the scope is up here in this controller tags. Okay, so and the dual load cell was just the name of the that I gave it when I originally created this ladder logic. When I went into RSLogix and I created this for the first time, I named it dual load cells because I got the two load cells connected. So that's what I named it, and that's why it's showing up there as the scope of that. But if we click down on this, we can then see this is my main program, which has the program tags. All right, and so when you select main program, then you're going to see all the tags that I created underneath of that main program. All right, so my filtered tags, my unfiltered tags. So now I can come in here and I can select some of these. And you got to be careful. You don't want to just select everything because you just have too much. So what I think I'm going to do is I'm going to add the total weight, which is unfiltered, and the total weight filtered. All right, so that's just going to give me two trends or two traces that are going to be filtered there. And then I'm going to click on finish. So now you see here's the graph, and you can see the timeline down here. Remember, I set the timeline to be 10 seconds, which really isn't all that long of a time. So you can see it actually puts the time here. So it's 6:33 p.m. And then the newest is 6:33. Well, they're both 6:33 p.m. Okay. Did I put 3 seconds? I thought I put 10 seconds there. I did put 10 seconds, so it shows me that right there. But at this point, it's not graphing anything, and so it's really not showing you that. But when I actually start this, you see right here, it says there's a run button that says start the trend. Okay, and then there's a stop button to stop the trend, and then there's like some errors here. But, so what you'll have to do is come over here to this trend now, and then press run to start it. So what I'm going to do is I'm going to go ahead and download my routine, or actually my main program, or you're really downloading all your tasks, but I just have the main program with the two routines. So I'm going to download it, and as soon as it downloads, then I'm going to click run. Okay. Well, I'm going to have to click on the run pop-up box first, okay, because I'm downloading, right? So I'm downloading, and it's going to say, do I want to run? All right, and I'm not going to click that quite yet. But when I click this, then I'm going to click run here, and I'm going to try to capture it as it's starting up. And the one thing that the reason I zeroed this out, the reason I went back over to the CLN and downloaded it and come back here to just zero everything out, was I want you to look when these two trends first start, what you're going to notice is that they, that filtered one is going to take longer to get up. So you're going to kind of see it sort of climb up. All right. And so that's kind of why I wanted to zero it out so we can see that. So what I'm going to do here is I'm going to actually say no, because I'm not quite ready on this, because I forgot I didn't change my scaling here. So if you double click on this, you can set the range of your y-axis. So remember that my scale is actually going from like 0 to 2.5, 2.6 pounds. So it has this automatic setting here, but you kind of have to be careful with automatics, because right now they're starting out at 0. And then it's going to jump around. So if you leave it on automatic, sometimes it jumps around and it doesn't quite show you what you're looking for sometimes. So how I got this, and you can get it a couple of different ways. You can just come over here. You can right click and go to properties. And then under properties, then you'll have general properties. You can have, display, so you can set the background color if you want. You can set the text color. So it looks an awful lot, right? If you remember what we were looking at in Factory Talk with the HMI, it really looks, because it's the same. It's all Allen Bradley, so it's about the same. We can come to the pins, and the pins allow us to set the colors. Okay, and this blue is kind of hard to see on this black background. And so I'm going to change it to a red. Make it it's a little bit brighter, a little bit easier to see. The green shows up pretty good, but that blue is really kind of hard to see. You can also increase the width on here, and you can set some other things. Okay, and you can set them visible or invisible as you go along here. All right, but then you can come to your x-axis, and this is where you can change and see. I set the trend period to be 10 seconds, but it's only showing 2 seconds on the screen here. So I don't know. I guess I'm gonna make it 5 seconds. Okay, I might want more than that, but we'll start off with that and see how that works. So that's going to be 5 seconds. Then I'm going to come over to my y-axis. I'm going to say select minimum is going to be 0, but the maximum is going to be 3. Okay. All right, so you can see here we're going from 58. Okay. Let me just make sure it took my values. So my x-axis was supposed to be 5, and my y-axis is going from 0 to 3. Now remember, this is in pounds, right? The units of this is actually pounds, because I've already scaled my weights. Or actually, no, wait, I'm looking at the total weight, so that's not going to work. I'm glad I looked at that again. So the total weight is 5 pounds. So I'm going to go from 0 to 5. I'm going to make it, I'm going to make it 6 pounds. All right. And the reason for that is because we know the unfiltered one flips around a whole bunch. So I'm going to go ahead and make that 6 pounds. All right. And so the filtered is green. The unfiltered is red. All right, and so I'm going to click over here, and I'm actually going to switch into run mode now. And as soon as I do that, I'm going to click run on my. Actually, I'm going to click run over here. I don't know if it's starting or not, but and then I'm going to go to run mode. I think I have to do it after. No, it does look like it's running. All right, so it is running here. 0. It only went to 3. Shoot. I thought I changed that. Properties, x-axis 6, y-axis 0 to 6. Oh, I put 6 in the wrong spot. Shoot. Okay, so so I missed that beginning. Let me see. Hopefully I captured it. No, I don't. Or maybe it just jumped up real quick. All right, so I didn't quite capture the bit that I really wanted to there, but I might have to build a little fill-in circuit piece or something here. But as we run this now, are you triggering? Was there a question? Okay. Everybody okay? All right, so no data in the trend. Where did my data go? Hold on. Okay, so this program should be running. Let's try this again here. Properties. Let's set this, the time span back to 3 seconds, and this should be 6. All right, because my totals are right around 5. It says it's running. I guess maybe because I have this period 10 seconds here. Let me change that. Continue scroll. Let me just download it again and see if it, don't know why it's kind of stopped going there. Always does this. I was doing this morning and I was able to stop it and restart it and it worked fine. And now that I've got you guys all online, it doesn't want to do it here. So, all right, so that's running. Let's click run here. Oh, there they are. Okay, maybe I just needed to wait for it a little bit or something. Okay, so you can see the green, and then the green is not moving, right? Because the green is the filtered, but the red is moving. Okay. So, oh, I guess, okay, all right, I've got my numbers backwards. That's what it was. Okay, so the periodic, this is how often I'm taking the sample, which is only every 10 seconds. So I do want that to be faster. I'm sorry, that, I was thinking that 10 seconds that I set up here was for my display. That's where, yeah, so let me go back to properties. So, okay, so the x-axis The time span, I want to be, I don't know, say at least 10 seconds. Okay, but the sampling, I do want sampling to be 10 milliseconds. I'm sorry, when I was trying to set that, I was trying to set this to 10 seconds, and I set the sampling to 10 seconds. That's why it didn't seem like it was collecting data, because it was collecting data every 10 seconds. And then as we know from, you know, doing our little timers exercises in class, you know, even a 5-second timer when you're sitting there waiting seems to be forever. So sampling is how often it's going to plot a point on here. So I was doing it every 10 seconds, right? So that was all 1001, 1002, 1003, 1004, 1005, right? All the way up to 10 before it actually created anything. So that's why I wasn't waiting long enough. So your sampling, you want to be fairly quick. Now, the catch is if you make sampling too quick, you overload your computer. So that's why they give you these different choices. The other thing is, you know, sometimes you don't need it to be milliseconds. So if you think about your, let's say that you want to graph putting, you're putting water in a 10,000 gallon tank, right? Well, it's going to take, you know, minutes or even hours to fill up a 10,000 gallon tank. And so therefore you don't really need to probably sample at a millisecond speed. But I want to try to capture that noise, and so I want to have it pretty fast here. So I'm going to make 10 milliseconds. And okay, so x-axis is going to show me 10 seconds, and we're going from 0 to 6 pounds. All right, and now when I hit run, there we go. So you see the red is the unfiltered, and it's bouncing all over the place, right? This is noise. That's what I was trying to show you, okay? So the red is the unfiltered, and it's just all over the place. It really displays it really nice when you do this. But the green is the filtered, so I'm running, right? The green is what we're running through this filter block here, and it looks really nice. And the trend, it's barely moving at all, so it's nice and solid. So that filter block really does a nice job getting rid of all this bouncy noise that we saw when we did that lab. Okay. So any comments or questions about this? Okay. So again, the sampling time up here, I set it to 10 seconds because I thought I was setting the screen range to be 10 seconds. Okay. And that's why I was like, why isn't it doing it? Well, it was trying to. I just wasn't giving it 10 seconds to plot a point. But now I'm plotting a point every 10 milliseconds, and you see it just bouncing all over the place here. Okay. I guess that red is still kind of dark for you guys on the screen. It looks way better on the main screen. I can see the red and the green very well. They're both kind of faint for you guys. Okay. But this trending, you know, it's almost like an oscilloscope that you can go in here and you can plot whatever you would like to see. And so it's kind of very, very handy there. Okay. All right, so let me just do one more thing here, and then I'll go back and I'm going to go kind of through the old exam or whatever and just remind you of some questions for the exam. But before I do that, okay, so notice the trend stopped automatically because I went offline, so I'm not talking to the PLC, so my data is not valid anymore. But what I want to do here in my main routine, okay, is I'm going to, actually I'm going to come to tags and I'm going to add a virtual bit. Which of course is of type Boolean. And then I'm going to add a rung to zero out Okay, so the very first rung here, what I'm going to do, because I want to zero this back out, because I want to try to capture that very beginning when it starts, because I want to show you the slowness of the filter if I can capture it. Okay, and so I'm going to add a rung. I'm going to make it the first rung, actually. And on this rung, I'm going to put this virtual bit. Okay, so here's this virtual bit. And then I'm going to put a move. I'm actually going to do two moves. I'm going to move 0 into weight 1. Okay. And then I'm going to put a 0 into weight 2. So just to zero it out, this is probably much more efficient to zero it out than trying to download the other program and all that, because here I can just zero it out on a fly. Okay, so I'm going to go ahead and download this. Okay, so when I turn on the virtual bit, then I can zero that out. Okay. Although since I've just downloaded the program again brand new, it should be zeroed out to start with. So I'm going to just start by looking at the trend. Okay, so let me pop up the trend window. All right, and then I'm going to go to run mode. Okay, so that did not zero that out. So I'm going to come over here and I'm going to go to this tag under edit tags, not edit tags, under monitor tags, I'm going to set my virtual bit to a 1. Okay. And so now my weights, okay, my weights did not zero out because I should have tied this virtual bit into the compute statements also. Okay, but notice here for my virtual bit, I'm going to make that a normally closed. Okay. All right, so what was happening here, this is standard ladder logic. Remember, ladder logic starts at the top, executes this, and then it executes this. So I was setting it, when I set my virtual bit to a 1, it was doing the moves, but then it was also, the very next 2 rungs, it was calculating the weight. So it was overriding weights with the true weight. So that's why I needed to put these bits over here. So we'll download that. That's a good test question there, actually, now that I think about it. Give you some ladder logic here with and without this and ask you what is the value. I really like that test question, as a matter of fact. Okay. So does everybody understand why I had to put these virtual bits here on these computements? Dave, to your question there, is the trend recordable? Yes, it is. Okay, so if we look at this, you see it has a logging option. Okay, so you can save this trend, or you can, another thing to just make a note, you can export this, which exports all your settings, so then you could upload them into another program. Okay, the only catch is your tags would have to be the same, But yeah, you can definitely log this information. Okay. All right, so I'm going to go ahead and click run there. Okay, so my program is running, and again, look at this green. This green's not moving, right? It's just right there at 5 or 5.1. Okay, it's not moving hardly at all. Okay, but okay, so I'm going to come to my program tags. I'm going to force my virtual bit to a 1. Okay, so my virtual bit is a 1. So now notice my weight. Oh, let me get back to the graph. Notice notice how the green is trailing off. Okay, let me stop this and see if I can go back here a little bit. Oh, it's not showing it. Okay. All right, so but you notice that it was like trailing down there. All right, so now they're both at 0. All right, so they're both sitting down here at 0. But when I come back, I'm going to turn this back to a 0, which is going to allow it to read the value in. But what I want you to pay attention to is the red is unfiltered, other than the little 5 hertz filtering happening at the input card. And so the total weight unfiltered, the red, is going to jump all the way up to 4.7 to 5.6, or and bounce all around immediately. But the total filtered weight is going to move very slowly. Okay, and so it's going to rise up much slower. So let me flip this to 0 and then get back to my trend real quick. And you see how, boom, the red, that red jumped. As soon as I turned it on, boom, it jumped up there to that value because it's essentially unfiltered. But this green is taking a while before it's getting up there. That's the filter action, and this filter is actually kind of slowing it down. And so the value is not accurate. The green value is not accurate until it's had a time for the filter to because the filter is like looking at all this data and averaging it, and it's taking a very, very long time to do that. Okay, so now remember, when I hit run, it jumped up because we were just looking at the graph, but the filter had already gotten up there. Okay, and so that's why once I hit run again, it jumped immediately, because the filtering had been done and it got up there. So again, if we come back here and I set it to a 1, set this back to a 1, flip back to my trend, right? The red immediately jumps back down to 0, but the filter takes a while to get down there because it's kind of trying to forget everything now. So there's a filter, a digital filter like this has a memory effectively. Remember that delta T that we talked about? The delta T's got to kind of time out until it forgets everything, because as long as there's some residue in there and it remembers, and so it takes it a while to react. All right, so let me I'm going to change this one more time. We'll watch it go up. Okay, and actually, before I do that, let me come back to the difference, come back to the trend, and I'm going to set the property. I'm going to set it, the x-axis was at 10 seconds. I'm going to set this to about 40 seconds. And the reason I'm going to do that is I want to see exactly how long is it taking it before it gets up there. Okay, and I think 40 seconds probably too long, but so I'm going to come over here and I'm going to set this back to 0, and then I'm going to come to my trend. All right, and I'm going to be able to stop it now, and we'll be able to see how long does it take it to get up there. All right, oh boy, this is like taking forever here, right? I mean, this is a long, long, long time here. Oh, there's a little missive, just a little bit there. So, but notice here, it took almost that whole 40 seconds. It took almost that entire 40 seconds for this to get up to about where it should be. Okay, and that's that filter piece going on. Okay, so it took almost 40 seconds. However, okay, I'm going to come in here. Remember, one of the things in my filter was the frequency. So I'm going to pop into tags, and I'm going to change the frequency. I'm going to speed it up. So I'm going to change the frequency from 0.1 to, let's make it 5 times as much, 0.5. Okay, so I've increased the frequency. And so now I'm going to set the filter to a 1 and run this. Okay, and boy. All right, so now we're down to 0. I'm going to pop back up here. I'm going to set it to a 0, or back to a 0, and go to my trend. You see how much faster it is now? Okay, so as you adjust your frequency on that filter, okay, before it took like 40 seconds to get up there. Now it got up there in just a couple of seconds. However, notice how it's bouncing all around now. When it was at 0.1, this line barely moved at all, right? The green line barely moved. But now, by increasing the frequency of the filter, I'm letting more of the bounce and more of the noise come through. So it's bouncing all around. Not nearly as much as without any filtering, but it's moving a lot more. Okay, so Robert, I just or James, I just saw your comment there about the filter. Yeah, that's correct. When we look at the ladder logic, sorry, I've got that on the other screen, so I didn't see it there. But when we look at the ladder logic, right, when I make the virtual bit a 1, then these are zeros, so it doesn't do the computes. But if these were not there, then it's going to do the compute all the time. There's no control of the compute being done or not. You're correct. Okay. So like I say, I think that just doing that right here, I just kind of pictured, hey, there's a couple good test questions. And kind of give you this code with some values and then ask you, you know, after one scan, what's the value with and without these bits here. So hopefully everybody understands what's happening there. Okay, and if you don't, now's the time to ask. Okay. All right, so but you see this, you know, this trend number 1 is kind of a nice tool that we can use to go in and see these analog, especially for analog values. See, for binary values, it's not all that interesting most of the time because it's either a 1 or a 0. It might be nice sometimes to look at it, and especially when you got multiple values, and see if they're all lined up there together, but for analog values, the trends make it really nice to kind of see what's happening and stuff. And now we can see again, by changing that filter from 0.1 to 0.5, the filter responded faster, so it got up to about where it should be faster, but it's also allowing more of the noise through, and so my value is bouncing around more than it did with the 0.1. Okay, so there's, you're like, well, why don't you just filter everything? Well, it slows down your response, and we're going to talk about, after the exam next week, we're going to get into talking about closed loop response. And that graph, I should have saved that. That graph, it was taking so long to get up there, and that means that any kind of disturbance in your system, it takes a long time to respond to it, and that can cause instabilities in your control. Okay, so that's just kind of a lead in to where we're going next week. Okay. All right, so anyhow, but that was the function block stuff that we talked about, and so I've got this recording now, so I'll post this so you can kind of go through all this stuff again if you want to. I don't think I'm going to put any trending on this. I won't put the trending stuff on this exam, just the function block diagram stuff. But trending will then this graphing and these sorts of things will definitely show up on like the third exam, because we're going to be talking about more here starting next Tuesday. Okay. By the way, while I'm mentioning it, there is lecture next Tuesday at 5:30, and we're going to start talking about closed loop control as the topic. Okay, James, I have not heard anything. The president did actually send us a message today. She did not mention any time about when we'll be returning to the classroom, so I have not heard. But I have kind of been hearing some of what the governor's been saying. I don't know if you're aware, he's been doing talks at 2 p.m. like almost every day since this started. And the way they're doing projections out into June about this virus is still going to be around. And so I have no say in it, but I would not be surprised if if we're going to be doing this for a while. So yeah, about the robotic vision. Yeah, I want to talk with you. I'll be sending you and those others in the robotic vision class an email here later this week to address that, because I'm really wondering now at this point if we will be back in the classroom in time to stuff. We might be, but I don't know. It seems like this virus stuff has really kind of just started, so. All right, so if there's no questions on function block diagram stuff, then I want to go ahead and flip over here. I have the first exam. The solution, this exam is posted in Blackboard, so hopefully you guys already went through this, but I just kind of want to go through here as a review for the exam. And then, and then just, I guess, any other questions that you might have. And that'll be it tonight. So, all right, so just looking, now if you remember, actually the first part of the exam was in Blackboard. All right, so this is just the 2-page written portion, which for us now, it's all going to be in Blackboard, right? So All right, so, but anyhow, looking at this, we have the first question was just looking at the grounds, and this, gosh, I think this was way back in week 1. Okay, so, and a lot of people tend to miss that first question because I think they just don't review that part. They just kind of skip over it. Okay, but there's basically 3 ground symbols that are used in schematics for control systems. The main ground symbol is this one here with the 3 dashed lines kind of going at a triangular sort of shape. And those basically, I would have kind of taken any of these 3 terms. Sometimes people call that earth ground, AC ground, but really I think the most correct term is power ground. So if you think about your electric motors and your heaters and your conveyors and everything, the things that are drawing lots of current, okay, those need to have a separate ground than your sensors. And otherwise we get all that noise in there. So we talked about that, like I say, way back in week 1. One of the things we talked about was noise and how noise can get into your signals, your AC signals and things. And I mean, we were just looking at noise, right? I mean, where to go here? Right, this is noise. All this bouncing around in this red here, that's noise, right? I've got a 5-pound weight sitting on those load cells. That weight isn't bouncing around like this. This is noise being injected into the sensors from these noisy power supplies that I have powering my PLCs, okay? And maybe other places too, but that's at least part of it. So, the weight isn't bouncing around. Like I say, the weight's just sitting there. It's pretty, I mean, there may be slight vibrations in the building due to, and C205, how noisy the air vents and stuff. So there's some vibration that might affect that. But all this very high bounce in this red here is a lot of that, I think, like say, comes from the fact that it's a switching power supply, so it's a very noisy power supply. I'm working on trying to buy some new ones that aren't quite so noisy, but anyhow, so we want to have all our high current stuff running to a separate ground to help minimize the noise. All right, and so our instrumentation ground, where we're going to be wiring our sensors and our analog to digital converters and all that stuff, should be a separate ground, and it's just a nice simple triangle here. And then this other one is the chassis ground. So you think about like that, the PLC, and we talked about it's got that 17-slot chassis, and that 17-slot chassis or whatever has a ground to it, which is the chassis ground. So these are just the various symbols that represent that. Okay. All right, so another way to get noise is inside of a cable. Now remember, we did also, week 1, we talked about the definition of a cable. A cable has 2 or more conductors within the same insulation. And the problem with that, even though you may have shielding around your cable to help protect from noise from outside, you've got those 2 wires running beside each other, or maybe even more than 2 wires running current in them beside each other, and that's injecting noise from one conductor to the next, and that's called crosstalk. And so so by twisting the wires together, we minimize that crosstalk. All right, and it's very important there to get the full 2 points on that. You had to say minimize. If you said something like eliminate or remove or whatever, we don't really remove the crosstalk. Unfortunately, there's always going to be some there. But by twisting those wires together, we can help minimize that crosstalk. All right, so the idea is to try to minimize noise. We would love to get rid of noise. That would be great, you know, but in reality, it's pretty hard to get rid of it entirely. There's always going to be some noise there. And like if we saw with that filtering, right? If you do much filtering, it eliminates the bulk of the noise, but it also slows down the system, it slows down the response, and so there's detriments there. All right, this is a binary timer. I don't know if I passed this around to you, but I actually have a physical timer you could wire up that has these little dip switches on here that you can flip. And so, but this is basically a binary to decimal conversion exercise. So you've got these little dip switches you flip on or off, and they're effectively a binary timer. And so when you flip it on, that gives you those numbers. So we have 2 is on, 8 is on, 7 is on, and 8 is on. And you add those all up, and you should have come up with 202 seconds. And of course, the units, you should always, if there's units applied, you should always have your units there. Okay. So, you know, you make sure you pay attention there. Honestly, for a lot of your questions on the exam, they're going to be multiple choice, and so you don't have to worry about them, but there will be a few fill in the blanks. So make sure if they need units, you put the units. Okay. All right. Process parameters are those things that we're trying to measure. So we're going to build a sensor or a transducer to try to capture information about these process parameters. And so I just listed, I only asked you to give me 1 on the exam, but I put 4 here. Pressure, flow rate, the level in a tank, the temperature, the current flowing into a motor. Any of these things could be a process parameter we want to monitor. Okay, so a signal converter, or sometimes they call them signal conditions, but is really using it as a converter, can convert a voltage signal, say 0 to 10 volts, or 0 to 50 millivolts into a current signal. All right, so if you have any questions as I'm going through this, make sure you stop me and let me know. All right, so question number 6 was dealing with that symmetric 4-bit analog to digital converter that we talked about, and I gave you that circuit. Okay, so let me maybe just pop over and get that circuit. So that was here under analog cards, if I remember correctly. I had the analog to digital and digital to analog converter circuits. Okay. And so this was that circuit. I figured it'd be that. Okay, so this was that circuit. And remember that every one of these that I've ever seen, we use a voltage divider. And this voltage divider is symmetrical, where we have, and the actual values of resistance might be different. Actually, they're definitely going to be different. They're probably more like 10K or even 100K, and then 200K, 200K, and then the top one and the bottom one are always the same value. And then the other values are basically double whatever the top and the bottom values are. All right, and so so that's what I mean by symmetric. The fact that it's 1, 2, and then 2, and then a 1. And there may be a lot more 2s in here as we go up from a 2-bit to a 3-bit to a 4-bit to 16, 14-bit, or with the one we have in the classroom is a 14-bit. Okay, so there's the very top would be a 1K, or 10K, or whatever the values are, but a 1 and a 10, and then all the other values are 2s in there. But that's that symmetric piece. And so if you remember when we ran this, I actually ran this for you in the classroom, and I also gave you that in the Blackboard. I showed you this in Blackboard, just right here. You know, the first, your resolution is your bit resolution, but the very first value is only half of that. Okay, and so so you kind of need to remember that, and that's because that first value is just a 1 there. This is a 1 or 10 or 100, and then this value is twice that. Okay, so that's what this question then on the exam was looking at. Oops. So the resolution, it was 4 bits with a range of 5. So I show you that since it's 4 bits, we can go anywhere from 0 to 15. So it's 5 divided by 15, which is 1/3 or 0.33333. So that's your resolution. The first detected voltage is 1/2 of that. The second detected voltage is this value, the 1/2, plus 1 full resolution count, which gives us the 5 volt. All right, and so that's kind of what this question was getting at. Okay. All right, so then number 7, an analog signal varies between 2 limits. I already made another point about that. Okay. Number 8, we're just doing the hexadecimal, counting in hexadecimal from 0 to F, and counting in binary from 0 to 15. So remember, in hex, F is 15 in decimal. Okay. And then we just did binary conversions. Okay, and then I even gave you a bonus question here to do a 5-point or a base 5 conversion. I was pretty happy. Most people were able to do that. I think just a couple people missed that or didn't even attempt it. So, but that was a bonus question on there. All right, so that was the written portion of the first exam. Okay, any or all of these questions are free game on Thursday's exam. Okay. So anybody have any questions there? Okay, it is 7:23, so I had no idea it was that late. Having fun here, so I guess I'll kind of, if you guys want to sign off, that's fine. I was pretty much done. Review the multiple choice kind of questions on the exam. I will be giving you, like I say, a lot of them are going to be multiple choice questions. A lot of them are some of the questions you've seen already, either on the homeworks or on the previous exam. So go back and review that. I'm keeping a very close eye on my email. So if you have any questions, email me. If you're having internet issues or whatever, call me. Leave a voicemail. My telephone number at school is 330-494-6170, and the extension is there. So I'll put that in the chat window. Okay, so there's my telephone number and the extension 4125. Call me and leave me a voicemail, and it's supposed to be forwarded to my email, so that because I'm not there at school, so you have to leave a voicemail, but you can call me and let me know if you're having any kind of problems. One other thing about the exam that I want to make sure I point out to you here is that the if you are having internet connection problems and you think you might have problem taking the exam for that, I could either email you like a PDF version of it, and then you could email it back, or if you think that won't even work, I can print out a hard copy. Give me your mailing address, and I can mail it to you, and you can take it and write it all down, and then mail it back. Okay. All right, but other than that, I'm done unless you want to hang around and ask some questions. Okay. But like I say, you can shoot me an email at any time, or send me a voicemail or whatever, and let me know what's happening, and just stay in touch.